Hello, 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 hello. So hi everyone. So so today's class will be discussing about more about the uh, ideal real gas equation. So before that, let me just briefly discuss the thing uh, that you have done in the last class. Okay, so just a second. So last class we have mainly discussed about the heat capacity heat capacity of solids mainly. So where we have basically discussed that the heat capacity of solids. So just a second. So experimentally it has been found out that the heat capacity of a typical solid looks like this. Okay, the qualitative behavior, this the qualitative behavior looks like. Okay, so what happens basically, so this is the specific heat and this is the temperature. Okay, just a second. Yeah, yeah, so okay, so this is how the typical qualitative behavior of a heat capacity of a solid material looks like. Okay, so here from the graph, as you can see, so initially the heat capacity follows T to the power cube law for the lower temperature, but after a certain temperature, that cutoff temperature, you can see the heat capacity of the particular solid basically attains a particular value, and that particular value is basically given by C equal to 3R. That is a constant value. Okay, now this is experimentally what has been observed. Okay, now to explain these things in terms of theory, at first Dulong and Petit comes up with this theory. So where they have considered the degrees of freedom per molecule. Okay, and you already know that the average internal energy associated with per degrees of freedom is equal to half into Na into kT. And so what they basically did, they calculated, sorry, not half Na kVt, it's half kVt, right? Half kVt. Yeah, yeah. So average energy, we know, associated with per degrees of freedom is given by half kVt. And for the solid, for per each molecule, you know, there is 6 degrees of freedom, and if there are 1 mole of material is there, so in that case the total energy would be Na into 6 into half kVt into Na into kV no R, so it would become 3RT. Okay, so in this way, at higher temperature, so this Dulong-Petit law basically able to explain their behavior at higher temperature, but this theory lacks at the lower temperature case. Okay, and to explain that behavior at lower temperature, what basically Einstein came up with the assumption that what what he actually assumed is that uh, he basically uh, he basically considered the vibration of the solids, the molecule in the solid, similar to the black body radiation. Okay, so in the black body radiation, as we know that each of the particle inside the like the black body basically radiation we can consider is a collection of photon, right? So each photon, we know in black body this each photon has, in black body radiation we know it's basically a collection of photon, right? And each photon we can consider each photon as a energy packet or as a quanta of energy, right? So each photon, we know each photon has energy in each nu, right? So nu is a fixed frequency of the photon, the frequency at which the photon is vibrating. Okay, nu is the fixed frequency. Okay, so this that means n is basically integer number. So this photon can basically attain any kind of energy state. N can be any integer value. Now, using the similar concept, what Einstein has proposed that each atom also in the solid, each atom vibrates with fixed frequency nu. Okay. Now, the similar way, just like the case of black body, here also, the average energy per degrees of freedom E bar, that is given by h nu by to the power h nu by kt minus 1. Okay, this is a very established result in black body radiation. What this is basically the average energy per degrees of freedom. Okay. Now for this case, for the case of solid, there are total energy. If you calculate the total energy, like if you integrate it, and from there you'll get some kind of this kind of expression 3RT into h nu by kVt by to the power h nu by kVt minus 1. And from here if you calculate the specific heat, this is a CV, specific heat at constant volume, that is would be dE by dt at constant volume. That expression you will be getting as CV equal to 3R into x square e to the power x minus 1 whole square, where x we are denoting as h nu by kVt. Okay. Now so we know, so this is the general expression of heat capacity. Okay, now we are interested in what is the behavior at high temperature and low temperature. Okay, to basically verify whether this expression is correct or not. Okay, so for that we have checked that for high temperature case, so here actually first defined a thing called Einstein temperature. Okay, theta e, that is given by basically h nu by k. Okay, and we basically write every other variable like x and all in terms of this Einstein temperature versus our reference temperature T. Okay, where we are basically observing the solid. Okay, now for high temperature case, where T greater than theta e, we have find out that the CV basically takes the value of 3R, which is consistent with the experiment. Okay, but for low temperature case, where T is less than theta e, we have shown that the CV basically follows some exponential kind of a curvature. Okay, so that means which is not basically there in the experimental case. Okay, so this is wrong basically, because experimentally it is find out that at low temperature C should be proportional to T to the power cube, not the exponential only. Okay, so that means, so there is some limitation with the theory of Einstein. So to fix that, Debye proposed another theory. So where the primary difference between the Debye theory and Einstein theory was that so in Debye's case, what he has considered, that instead uh, uh, of considering that each atom will vibrate at a fixed frequency, consider that uh, the vibration forms a continuous spectrum of frequency. Okay, frequency, and that spectrum has a maximum value up to maximum minimum. Okay, so this is the primary difference between the Einstein Debye theory. Okay, and here also he also considered that the vibrations are kind of acoustic type of vibration. Okay, acoustic means the vibration that when like sound when flows from air, so it basically obeys this acoustic vibration. Okay, it basically shows this acoustic vibration. So similar type of vibration he considered inside the solid also. Okay, that is basically the elastic waves. Okay, so these are the two considerations are there for the Debye's theory. Now, following this consideration, he basically calculated the average in the first he calculated the expression of this uh, yeah. So the expression of this total energy. Okay. So in the this is the expression of total energy, E bar into G nu d nu. So E bar is basically the average energy, and G nu is basically is the density of state, because there are frequency, right? So for each, so since there are like a range of frequency, right? So nu basically varies from 0 to a particular value nu m. Okay, so between nu to nu plus d nu, there are certain numbers of states will be there, right? So that density of states is basically given by G nu. Okay, this is the density of states. So if you basically multiply G nu with that uh, 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 particular volume, that is 4 pi, in the case of 3D 4 pi 3 nu cube, so that gives you the total density of states. Okay, so anyway, now from this way he has also calculated the CV. So he basically first calculate the expression of G nu, then now after that by doing the integration and doing the differentiation with respect to the T at constant volume, we got the expression of CV like this kind of expression. This is a very big expression, 3r into 12 pi xt cube x cube e to the power x minus 1 dx minus 3xt into to the power xt minus 1. Okay, where xt is basically h nu d by kVt. The nu d is the new thing that is known as Debye's frequency. Okay, that is given by yeah, the Debye's frequency, and xd is h nu d by kVt. And there is also a new thing, that is the theta d. Theta d is the Debye's temperature. Okay, the theta d basically given by h nu d by kV. Okay, yeah. So this is the Debye's temperature. Okay, there are two things here. One is the Debye's frequency, another is Debye's temperature. Okay, so these are very important thing in terms of solving numerical problems. So you can like in order to solve the problems, you have to remember these relations. Okay, what is the expression of Debye's temperature, what is the Debye's frequency, okay, what is Einstein temperature and all. So this is basically a very important. So in high temperature, similar way, it has been found out that high temperature, for both high temperature theta d, it shows that CV basically shows 3R. So it basically validates the experimental findings that we have observed at high temperature, and also in low temperature CV shows some functional form as a function of TQ. Okay. So that is in the low temperature case. Okay, so D-based temperature is D-based theory is basically consistent for both the case of high temperature and low temperature. So it's the most accepted theory till now. Now next we have discussed about the ideal gas equations. Okay, so sorry, not real gas equations. Okay, so previously the equation of motion, equation of state that we have used is this one: PV equal to NKT, right? NRT, sorry. Yeah. Now this is for ideal gas equation. Yes. Now for real gas, since there are interaction with there, the molecule of the gas also will have some volume inside the container. So if you consider all of these things, then this ideal gas equation reduced to this kind of equation. This is a virial expression. Okay, this is a empirical expression. So P minus V equal to RT. So this is the pressure correction term, this is the volume correction term. Okay, and this is known as the van der Waals equation. Okay. Okay. Yeah. This is the equation for real gas. Okay. Yeah. So now for this today's class we will be more discuss about this van der Waals gas equation. Okay. Now now in next class, last class also we have discussed about this isotherms. Okay, so we can basically using this van der Waals equation. Okay, we can basically calculate this critical volume and critical pressure of the from the isotherms of the of a particular gas. Okay, so if you write this van der Waals equation in more a kind of a quadratic, sorry, not quadratic, it will be a P equal to RT P minus B minus A by B square. For more reduce, if you reduce a bit more, so it will become P into VQ minus, plus PB plus RT V square on A into V minus B. Okay. Now, so now this is a very if you take V as a variable here, and P and V both are the variable, and you can take T as fixed. You can basically plot this equation, right? And for this equation, for a fixed P, there are basically 3 roots of V. Okay, so there are 3 roots. Since it's a V to the power cube equation, right? So there are basically 3 roots. If you basically equates 2 equal to 0, so in that case there are 3 roots. So in these 3 roots there are 3 possibilities. Either 3 roots are real, or 1 root is real and the other 2 roots are imaginary, right? So there are 2 possibilities are there. Okay. So now if you plot it for a fixed temperature, so the cases that you have considered for isotherms, right? A similar way, from this equation also you can calculate this isotherms, right? For a fixed temperature, if you plot this equation with respect to P and V, this plot looks like this. Okay, so for lower temperature, it shows some kind of this kind of behavior. If you make it higher, it will show this. Yeah. This is different temperature: T1, T2, T3, T4, T5. Okay, T1 is smaller than T2, smaller than T3, T4, like this. Okay. Now for lower temperature case, as you can see, there are basically three roots are there. Okay. These are the three roots. Okay. Now if you make the temperature higher, there will be a single root. Okay. The other two roots are basically uh, the imaginary one that would be not be there in this real space. Okay. And this temperature required basically this roots basically merges. Okay, so single root is there. This point is basically known as the critical point. Okay, this point, this concept of critical point we have already discussed in the last class, right? So um, so this is the point, the minimum point where the temperature and pressure and volume that is required to make the gas to condensed state, right? And if you compare this behavior with with actual experimental data, so experimentally what is this isotherms looks like this basically. Okay, if you saw at high temperature, it shows this is the ideal behavior. Okay, where the gas follows this kind of parabolic kind of a curve. Okay, now if you decrease the temperature, it shows this kind of behavior. Okay, but this plateau regions are basically uh, yeah, this plateau regions basically indicates the phase separation. Okay, so gas basically if you decrease the pressure and all, sorry, increase the pressure and all at a fixed temperature, so the gas basically changes state from gas state to liquid state. Okay, so this condensation state is basically denoted by this plateau region. Okay, but this is what has been observed in experiment. Okay, now like if you saw in this if you want to compare this experimental result what with our theoretical equation, then you can see there are some discrepancies are there. So the first one is that uh, this thing where this in between region where this PV diagram basically shows a plateau region which is basically absent in the case of this theoretical result, right? uh, yeah, so that is one of the discrepancies. Okay. Hmm. Yeah. And but it kind of shows us the critical point, right? So the in this point where this P is the critical point, so P is the critical point where there is one real root. Okay, so this critical point is basically well explained by this theory, this equation, this Van der Waals equation, right? So from using these Van der Waals equations, we basically calculate this critical point or root of the equation. Okay, now we will do that. So, so how to do that? Yeah, you can ask question if you want.
Yes. So in your graph, the critical point is on T4 curve, right? So
Yeah,
I was
right.
thinking, is T4 equal to T here?
Huh? T4 equal to
Is, yes, yes, critical temperature, TC.
uh, TC. Yeah, T4 is the critical temperature. Yeah, what you are saying is correct. Okay, T4 is the TC, the critical temperature.
Okay,
You are
okay.
referring it as critical temperature, right?
Yes, yes.
TC. Yeah. It is correct. Yeah. Okay. Yeah. So, so how to to get that point of this critical point? So there is a way actually. Okay. So if you study this curve carefully, so this curve looks like this. Okay, this kind of, right. So this is called the point of inflection. Okay, so this critical point P. Okay, point of inflection. Okay, so what does that mean? That means that this curve initially shows a concave type of a behavior. This curvature of this curve before this point of inflation, it shows this concave shape, and after this point of inflation, it basically shows a concave shape. Okay, so that means the curvature is changes. Okay, so that means so the curvature, if this is a function, let's suppose this is some function of f of p and v. So in that case, for the case of concave case, this double derivative with respect to p, sorry, with respect to v, since this is the, sorry, it would be like this. Yeah, p as a function of v. Yeah, so this is basically p as a function of v, right? This at a fixed t. Okay, so now in this case, the double derivative of p with respect to v uh, would be smaller than 0, and in this case the double derivative of p with respect to v will be greater than 0, and at this point of inflation, this p double derivative with respect to v, d square p dv square at a fixed t will have a 0. Okay, so yeah, so basically, so that means, so basically using this condition and the condition of the extremum case, okay, that is del p by del v at t equal to 0, we can basically calculate this point of inflation. Okay, so first what you have to do, write this thing p as a function of v, that is from the van der Waals gas equation, and uh, so first, so these are the two conditions. So dp by dv at fixed t is equal to 0, so that basically gives minus RT by V minus P whole square plus 2A by PQ equal to 0, and double derivative of P with respect to V at constant T gives equal to 0, so that will gives you 2RT into V minus B whole cube minus 6A by V to the power 4 equal to 0. These are the two equations, right? So from here you can just doing some rearranging of terms. So we can write this RT from 1, RT by V minus V whole square equal to 2A by V cube. Okay, now this thing, okay, you can, this from this thing, the expression of RT, you can substitute it here, and after doing that substitution, okay, you will get so these are all, this all thing is happening at t equal to tc. Okay, so t equal to tc. Okay, yeah, so that means the volume, that expression that you are getting, that would be 3v, that is nothing but a critical volume vc. Okay, yeah, so now we get the expression of vc, right? Now if you just simply substitute the vc expression here in the equation 2, that would give you the expression of TC. Okay, so TC would be, so this would be the expression of the TC. Okay. Uma, কাকা একটু ফোন করছেন। Hello. Yes, yeah. So T equal to TC. Okay. Now similar way, so you got TC and VC expression now. Uh, you have to so you got the expression of TC and VC. Now from here, if you substitute the expression of TC VC back into this original equation by van der Waals, from there the expression of PC you will get PC equal to A by 27 B square. Okay. So these three are basically very important quantities. Okay, PC, VC, and TC. The critical critical point. Okay, PC, VC, TC. Okay, so these three expression you have to remember. Okay, for van der Waals case, this expression of PC, VC, and TC. Okay, you can also there is calculate the ratio of these three things. C, that is R by TC into PC by VC. So this is a dimensional, non-dimensional thing. That would basically gives you 8 by 3. Okay. That is uh, close to 2.666. Yeah. Now for ideal gas case we know C equal to 1 for ideal gas. Okay. Now there are actually different types of gas equations are there, like just like van der Waals. Van der Waals is the most accepted one. Now apart from van der Waals, there are other scientists who have proposed different types of gas equations, like the state equation uh, to basically explain the behavior of ideal gas. So for those equation, this value of C would be different value. Okay. For the case of van der Waals, it's 8 by 3. Okay. And for the case of ideal gas equation, it would be equal to 1. Now one other thing that you can also do, so we have already calculated PC, VC, and TC in terms of this constant A, B, and C. Okay, so we can also do a reverse. So you can write this expression of A, B, and C in terms of PC, VC, and TC also, right? So VC equal to 3B, TC equal to 8A by 27 RB, and PC equal to A by 27 B square. Okay, now from here you can calculate TC into PC equal to 8A by 9R. So from here A equal to 9R by 8 TC by VC. Okay, similar way you can also calculate yeah. So also you can write it like you know VC also. Okay, so uh, VC is there. So VC is yeah. Hmm. Now this is the way. Now also you can calculate the other things also, right? You can calculate P also. P would be VC by 3. So you can substitute. Also you can write yeah. Hmm. Hmm. Yes. There are certain ways. There are many other different ways also, right? You can also write A in terms of PC also, PC VC, PC TC. TCPC. Okay, so the different way you can write basically the expression of A according to your convenience. Okay, I mean according to the nature of the problem. Okay, yeah. So now, okay, now we'll be showing this. This is a very important thing, the virial expression of the van der Waals gas equation. Okay, so first we'll only show the in terms of volume. Okay, so there are two ways basically. You can write this virial expression expansion in terms of volume also. You can also show in terms of pressure also. So this is a very not so difficult way. So E equal to E by P plus A by V square to V minus B equal to RT. So in order to do this virial expansion, okay. What you have to do, P plus A by V square equal to, take V as common, 1 by B by V equal to RT. Then from here, V into P plus A by V square equal to RT into 1 minus P by V inverse. Now we know that B is simply the co-volume, right? Which is uh, so basically the B is much smaller than the V. Okay, so B by V also much smaller than 1, right? So we know that from binomial expansion, that if 1 plus x inverse, we can write this thing as 1 plus x plus, sorry, 1 minus x, 1 minus x, 1 plus x plus x square plus x cube, provided the condition is x is smaller than 1, right? Mod of x specifically. So so same thing we'll be using here, right? Same concept. So uh, you can write it as PV plus A by V equal to RT into 1 plus P by V plus V square by V square plus P cube by V cube plus, there will be other higher order terms. Okay, so now PV will become RT plus RT V minus A plus RT V square by V square plus, there will be higher order terms, right? Yeah. Now you can also take RT as common, right? So PV equal to RT if you take common. So this expression will become like this. So 1 plus can write this thing as beta. Okay, beta by V gamma by V cube, sorry, V square plus the other terms. This beta gamma, this is called the second order. This is the second order coefficient. Okay, yeah, I mean whatever the way you can write this expansion. Okay, yeah, this is a different way. Okay, so you can basically, using this equation, you can basically ignore the higher order terms to basically uh, to basically approximate this equation in a useful way. Okay, and yeah, so what you can do here is that uh, if you let's suppose you only consider the term up to the first order coefficient. Okay, so only up to this you consider PV equal to RT plus RT by B minus A by V. Let's consider the volume is very high, the container volume is very high compared to uh, the co-volume of the gas fluid, like gas molecule. Okay, so you can basically neglect this higher order terms, right? You can consider up to the first order term. Now from this equation, what is the condition? Okay, what is the condition to get back the ideal gas equation, right? So to get back the ideal gas equation, what you have to do, you have to equate this term equal to 0, right? So that means RT by B minus equal to 0. So that means T would be A by uh, RB, right? So this T basically known as the Boyle's temperature. Okay. So this Boyle's temperature is a very important temperature because at this temperature, if you neglect the higher order terms, this real gas basically behaves like a ideal gas. Okay. This is a very important, also very important quantity to remember. now Now we'll discuss there are some limitations of the of this Van der Waals gas equation. Okay, so here what the first limitations is that in that equation they have considered that A and B as constant. Okay, but in experiment different gas has different values of AB. Okay, so in that case AB simply are not constant. Okay. Also this critical coefficient that you have this C this that you have calculated, this C thing, this is known as the critical coefficient. Okay, critical coefficient. So this experimentally calculated value of this critical coefficient C is not is in between 3.1 to 3.9. Okay, depend upon a different species of gas, but from the Van der Waals gas equation, we have seen that the C has a fixed value of 8 by 3, which is not true. Yeah. And the third thing is that, yeah, third thing is that same thing. Okay, so this critical volume VC that we have calculated is just 3 by B, that is some constant. Okay. Now, uh, this is the expression of the VC, but in observation, it has been observed that the VC basically varies from 1.46 to 2.86. Okay, that means it is basically a variable thing. Okay. So this is the limitations of Van der Waals gases, but still in some way uh, it is useful to basically approximate the gas behavior. Okay, although there are some limitations are there. Now we can also rewrite this Van der Waals gas equation in terms of reduced units also. Okay, so you can so in order to make the equation dimensionless, this reduced units are basically written in terms of this critical pressure, volume, and temperature. Okay, so reduced pressure PR is basically P by PC, PR is equal to V by VC, and TR equal to T by TC. Okay, so these are the reduced units, right? And if you rewrite this Van der Waals gas equation in terms of this reduced units, the equation will become like this: PR plus 3 by PR squared PR minus 1 by 3 equal to 8 by 3 TR. Okay, so these are the reduced modes, and this is the dimensionless form of the van der Waals gas equation. Okay. Yeah. So far we have discussed first about this. Yeah. So far we have discussed about the expression of PC, VC, and TC, right? What is that? Yeah. So this is the expression of critical volume, temperature, and pressure in terms of three constant, that is ABC, that has been that can be experimentally find out. Okay. And we also can write the opposite way also. You can write this ABC in terms of PC, VC, and TC also. According to the problem, we have to readjust these things, right? Next, we have also talked about the boil temperature TB, and that temperature, that gas basically, that real gas basically behaves like an ideal gas. And we also discuss about some limitations of van der Waals gas equation. And lastly, we have talked about that we can rewrite this van der Waals equation in terms of reduced units, which basically makes the whole equation in a dimensionless form. Okay. Now, and also we have discussed about the virial gas. Okay, this virial expansion of gas, right? Yeah, but you can also this virial expansion. Okay, I have not talked about this. So this virial expansion also you can write in terms of pressure also. Okay, like you can write this virial expansion. Okay, P equal to PV equal to RT 1 plus P into P C into P square D into P cube, like this. In terms of pressure also you can do this virial expansion. Okay. Okay. Now, so there are other equation of states also. So far we have only talked about this van der Waals equation of state. Now there are also other equation of states are there. One is this called this Clausius equation. Okay. These are some basically mentions. Okay, although they are not that much used compared to uh, van der Waals gas equation, still there's in some cases are important. So this looks like takes this kind of form. So here you can see there are this expression a bit changed. So here there is the volume comes in the denominator compared to the van der Waals equation, and there is also another constant C, right? Just a second. Yeah, this is the volume square. So here there is a temperature and also volume, right? Not volume square is there compared to the van der Waals equation, right? And there is also another constant, that is C, that is used here. Okay. And these equations basically will explain the Andrews result for carbon dioxide gas, right? That from there this measurement of this condensation thing uh, uh, is there, right? So that experimental result basically will validated by this Clausius equation. Okay. Next is the Barthelot's equation. This is also empirical. As you can see, compared to this Van der Waals equation, here you can see there is a temperature term T is there in this sorry, pressure correction term. Okay, there is a extra term, there is an extra variable T is also, temperature is also involved here. Okay, this is the Barthelot equations. Next is the Dirichlet diathesis equation. Okay, equation. This is theoretically proved actually. Okay, theoretical. So this equation is looks like this: P equal to RT V minus P to exponential minus C RT into B. Okay. Lastly, Saha and Bose equations. Okay. Theoretical. So this is also been theoretically proved using the concept of statistical mechanics basically. So here also uh, P is RT minus RT to be exponential minus A by RT V into log of V minus 2V. Now for so there are like for Van der Waals gas, this critical coefficient we know is 8 by 3, right? Now for all of these gas equations, there are separate calculation of this critical coefficients. Okay. So for this last two, critical coefficients values are basically for diathesis equation, this C is critical coefficient, that is RTC by TCVC is basically 3.695, and for the Saha-Bose equation, critical coefficient C is basically given by 3.53. Okay. Now for the case of Van der Waals, it was around 2.66, right here, 2.66. Okay. Some problems may come where it can be asked like the gas is following this Barthelot equations or Clausius equations. Okay, so according to that gas equation, you may have to calculate this different quantities, PC, VC, and TC. Okay, the process would be same like the process that we have used for the case of Van der Waals gas. Okay, now for this case, you instead of Van der Waals gas, maybe the gas followed some different equations. Okay, that would be mentioned in the question. Okay, so anyway, so these are the some, so that this those different equations. So these are the four other important types of equation that may can come. Okay, now we'll be discussing this concept of temperature scale. Okay, before that, let me first write the zeroth law of thermodynamics. Okay. So after the discovery of first, second, and third law, this new law comes. So they basically named it as zeroth law. So what this law states is that let's suppose uh, there are basically So if two bodies are in thermal equilibrium with a third body, so this body, so third body, then they also in thermal equilibrium, okay, with each other. So let's suppose there are two bodies, let's suppose A and B, okay. Now A and B both are thermally equilibrium with a third body, let's suppose that is C. So if A is in thermal equilibrium with C, and if B is also thermal equilibrium in C with C, so that means A and B are also in thermal equilibrium with each other. Okay. Now, so here, so to basically quantify whether this like two bodies are with whether they are thermally equilibrium with each other or not, to verify that, so they basically invented this concept of temperature. Okay, so that means if TA, temperature of body A is equal to temperature of body C and temperature of body B, in that case all these three bodies are thermal thermally equilibrium with each other. Okay, so in that case this concept of temperature basically becomes a very important quantity to calculate, to basically figure out whether the systems are like the thermally equilibrium with each other or not. Now, to calculate this temperature, this different types of temperature scales are invented. Okay. So this temperature scales basically measures a thermometric property. Thermometric property means that property that changes with temperature. Okay. So by calculating those property, basically you can basically calculate what is the temperature of the system. Okay, from how the thermometric property changes with temperature, by doing that calculation also you can calculate easily what is the temperature of the system. Okay, so for easy to understand, what they have done initially is that they have considered, so a thermometric quantity that basically varies linearly with temperature. Okay, so let X is a thermometric property that varies linearly with temperature. Okay, so X is basically thermometric, so X would be a function of theta. So here theta is basically the temperature. Okay, so instead of T, let's write it as theta. Okay, so X function of theta would be, since it's a linear property with respect to theta, so you can write it as theta plus B. Okay, now uh, so we are here, here we have basically two constants, right? So two parameters, you can say. Now to find out these two values of these two parameters for a certain type of material, what we have to do, we need two fixed values, right? So two fixed values basically gives us two equations, and from by solving those two equations you can get the values of these two parameters, right? So uh, so to get those two fixed point, we basically determine two of the easiest thing that you can calculate. One is what is the value of this thermometric property at ice point, right? Ice point, where basically water freezes into ice, so at that temperature theta is basically equal to 0 degree. So in that temperature you can calculate the thermometric property x0. And second will be at steam point. Okay, that would be theta as 100 degree. So that gives us the thermometric property at 100 degree, right? Now, so we got basically two equations, right? So x0 is basically theta would be 0. So from this equation, right, x0 would be v, right? Yeah, from this equation, and from this equation you will be getting x100 equal to a into 100 plus b. So you can write a as x100 by b, we know is x0, so x100 by x0 by 100. Now from here, from this equation, okay, from this equation you can write theta as a function of x equal to x minus b by a. Now b we know is x0, a we know is this. So if we substitute this, we can write theta x equal to x theta minus x0 minus x100 minus x0 into 100. So this means if we somehow calculate at a theta temperature, if you can calculate any thermometric property, there are different types of thermometric properties are there: length, resistivity, volume. Okay, different properties are there. So for a particular material, if you can calculate that particular thermometric property that we will be considering at theta temperature, okay, x theta, by calculating that, we can get that corresponding temperature, that is the theta, okay, using that particular scale. And x0, x100 are the fixed values, okay, that is like what is the temperature of that 0 degree, and what is the temperature what is the value of the thermometric property at 0 degree, and what is that property as 100 degree. That are some fixed constant values, okay. So by putting this and so by putting this into this expression, we will be getting the temperature of our interest, okay. So this is a very important quantity equation, you can say. So there are many kinds of properties that there. One is the pressure, okay, and to calculate that particular thermometric quantity, there are different types of thermometers are also there, okay. So if you consider x as p, in that case there is a measurement machine or the thermometer machine that known as constant volume gas thermometer, okay. So that instrument measures the pressure of the gas as a thermometric quantity, and from there, by using this relation, okay, 273.16, it can give you P by this P is some reference pressure, okay, pressure at some reference point, okay, and this P is the pressure at that particular temperature theta, okay. So by measuring this, you can calculate the temperature for that particular pressure, okay. Similarly, if you take volume, x as volume, so this instrument is known as constant pressure gas thermometer, okay. But pressure is constant and volume of the substance will change, okay. That's why it's named as constant pressure gas thermometer. In that case, the T theta would be a function of volume, right? 273.16 into V here. Similarly, you can also use the length X as length also. This is known as liquid thermometer. Okay. In that case, theta would be, sorry, yeah, sorry, these are pressure, right? Pressure, volume, and L. Yeah. Sorry, this theta, T is itself is temperature, right? So it would be pressure, volume, and length. Yeah. Pressure, volume, and length. So 270 divided by 6 into L into L. Yeah. Lastly, there are also another thing, that is the resistance. Okay, you can also use resistance also as a thermometric property, since you know the resistance of a material depends on to the temperature of that material also. So this is known as the resistance thermometer. Resistance thermometer. In that case, R would be R0 into 1 plus alpha T plus beta T square. Okay, so this is the way if you change the temperature. So there are basically two constants are involved, which basically dictates how with temperature how the resistivity of that particular material will change. Okay. Yeah. So how these expressions are basically coming. So for a constant volume thermometer, constant volume means here the thermometric quantity is basically the pressure, right? So it basically calculate the pressure at two different temperature. Okay, one is the reference temperature T0. Not this is not a reference temperature T0, yeah. And another one is the uh, T0 plus 100. Okay. So T0 is basically that is the, you can say, the temperature where this gas basically becomes ice point of that particular gas. Okay. And T0 plus 100. Okay. Now from there you can calculate from ideal gas equation, you can write this P0 by V equal to NR T0, and for this one you can write P100 V equal to NR T0 plus 100. Now if you equate these two equation, now from there you can get, now for our region, so so this is the two these two equations are there to calculate the fixed points. Okay. Now our interest is we want to calculate what is the temperature, what we will calculate the pressure at a reference temperature T, right? So from there itself we want to calculate what is that particular temperature T. So for that we will be taking some we will do the ratio with PV equal to nRT. Okay, so if you do that with 1 and 2, it will give you P by P0 equal to T by T0, right? Now from here T would be P by P0 into T0, right? Now also from 1 and 2 also, if you make a ratio of 1 and 2, then from there also you can write 1 by T0 equal to P 100 minus P0 by 100 into P0. If you substitute this 1 by T0 expression here, this gives you T equal to 100 by P100 by P0 into P. Okay. So in this way, if you calculate the pressure at two reference temperature P0 and P100, right, we can calculate the temperature where this P is being calculated. Okay. Yeah. Similarly, there are other ways. Okay. Similarly, for the case of this platinum or thermometer, platinum resistance thermometer also, R theta is basically R0 plus 1 plus alpha theta plus beta theta square. Now, if you reduce the equation up to the first order, for the simplicity, we can write this as R0 into 1 plus alpha into theta. Now, this theta is basically known as the platinum scale temperature. That is the temperature basically that is shown by that platinum wire. Okay, so that known as the platinum scale temperature. Okay. Now, by measuring this to measure this theta, similar way you have to calculate R as R at t equal to 0 and R as t equal to 100, right? Now from that itself you can calculate theta as R theta minus R0 by R100 minus R0 to 100. Okay. A similar formula. Okay. Okay, so now we'll solve some problems. Okay. So problem number 1. Calculate the van der Waals gas constants for hydrogen. Given T equal to 33.2 Kelvin, P equal to 12.8 atm. So the critical constants, and R equal to 0.082 liter 18 mole inverse Kelvin inverse. Okay. So you already know, right? So that means A, B are given. From there, we have to calculate the TC, PC, right? So TC we know. What is that? Yeah. So TC, PC, and BC3 expression you already know, right? So we will first write that. TC is basically given by 8A by 27 RB. PC is given by A by 27 B square. Okay. So now, so to write this B in terms of TC and PC, since VC is not given, so you have to use the TC and PC, right? So you have to somehow write B in terms of TC and PC, right? So from this two equation, if you take the ratio of TC and PC, what you will get 8A by 27 RB into A by 27 B square. Okay. So now from here you can write this thing as 8B into R. Okay. TC and PC. So from here you can easily calculate the value of B, right? So B would be simply R into TC by PC. That means 0.082 into 33.2. The units are all consistent, right? So Yeah. So if you calculate it, it would give you equal to 0.0266 liter per mole. Okay. So it is the, yeah. Yeah. This is, sorry, this is 18 to PC. PC was 12.8. Yeah. Hmm. Okay. Now similar way, you can also calculate the A. So you got B. So from there, using this equation, you can also calculate A. So A is basically PC into 27B square. So PC is already known 12.8. 27 into B square is B square we already calculated 0.0266 whole square. So it gives you A equal to 0.247. So A is this bar per liter square per mole square. Okay. Now the next problem is calculate boil's temperature of 1 mole of helium gas using the Van der Waals constants equal to 3.59 into 10 to the power minus 3 Newton 10 to the power 4 1 to the power minus 2. B is 2.41 into 10 to the power minus 5 meter cube per mole, and given R is equal to 8.31 joule. Okay, mole inverse, Kelvin inverse. Okay, the options are 15.89 Kelvin, B is 17.93 Kelvin, C is 21.59 Kelvin, and G is 19.85 Kelvin. So you know the boil temperature expressions is given by TB equal to A by RB, right? That we have shown, or that we have showed from the Fourier expansion, right? By equating the second coefficient equal to 0. So TB equal to A by RB. So AB we know already. So 3.59 into 10 to the power minus 3 into 8.31 into 2.41 into 10 to the minus 5. If you calculate this thing, so it gives you approximately 17.93 Kelvin. Okay. Yeah. Now question 3. Uh, second virial coefficient beta of a gas is 0.02 liter per mole. In that case, calculate the volume of 1 mole of the gas at 27 degrees centigrade and 5 atm pressure. The options for option A 11.2 liter, option B is 6.78 liter, option C is 5.11 liter, and option D is 5.72 liter. Okay. Now, since in the problem up to the second order virial coefficient is mentioned, so that means we can also use this Van der Waals equation, virial expansion up to the second order only. Okay. The other orders, the other constants like other virial coefficients are not mentioned, so we can do that basically. Okay, so we know the up to second order the virial expansion looks like this: R equal to 1 plus beta V. Okay, up to second order. That we have done, right, this equation. So this is the virial expansion, right? So we are writing basically up to this, up to the second order. Okay. So now okay, so we have to calculate the volume. Okay, so volume, as you can see, this is a basically second order equation. This will become a second order equation, right? So you multiply the V both sides, so P into V square plus minus RT V minus RT beta equal to 0. This is a second order equation. If you find the roots, the roots of the equations are basically the volume that you want to calculate, right? So the roots of the equation will have this root, right? RT plus minus R square T square minus plus 4RT P beta divided by 2P, right? So if you take RT as common, so you can rewrite it in a much simpler way. So 1 plus minus 1 plus 4P beta by RT whole thing is divided by 2P, right? Now from here simply just substitute the values of R and T. So R we know is 0. 0.082, right? 0.082. Temperature is 300 Kelvin, right? 27 degrees centigrade is 300 Kelvin. Pressure is 5 atm, so pressure is 5 atm. And what else needed? So these, I guess, these are the things that is only needed here. So just substitute all of these things here. So V into 0.082 into 5/300 divided by 2 into 5, 1 plus minus root under 1 plus 4 into 5 into 0.02 divided by 0.082 into 300. Okay, if you calculate this, the V will become 2.46 into 1 plus minus 1.072. Now you simply cannot take the negative equation, negative term, right? Because if you take the negative, then this whole volume will become negative, because 1 minus 1.078, so this whole term will become negative. So we cannot take the negative one. You have to, volume cannot be negative, right? So you have to take the positive term. So in that case, it will become around 5.11 liter. Okay, taking the plus B. Okay, so this would be the correct answer. Next problem is 4. Find the critical volume of a gas weighing the diathesis equation by P equal to, this is the equation given by P equal to RT V minus P e to the power minus A RT by V. Now, so you have to calculate. So instead of the Van der Waals gas equation, so here the gas basically follows this Dirichlet's equation. So it is given by this form. So for this form, you have to calculate the critical volume. So the critical, finding the critical volume, we will use the similar process. Okay, just like we did for the case of Van der Waals one. So option A is B, option B is 2B, option C is 3B, option D is 4B. Okay. So we know the equations is given by basically P equal to RT V minus B for V minus, sorry, RT by V minus B into e to the power minus A by RT V. Okay, so we know the conditions. dP by dV equal to d square P by dV square should be equal to 0. Both these two conditions needs to be satisfied, right? So okay, first let's do the dP by dV. So dP by dV gives you RT to the power minus A by RT by V into 1 by V minus B whole square plus A into RT V square by V minus B, right? So now dPV dV equal to has to be 0, so we can write this as, this term cannot be 0, we know, this exponential term. So you can write this as 1 by V minus B whole square plus 1 by RT V square V minus B equal to 0. Okay. Now if you can write this thing in much more simpler way by just multiplying V minus B whole square in both the sides. So by doing that, you will be getting A into V minus B into RT V square equal to 0. Multiplying V minus V square. Okay. So now you can write RT as A into V minus B into by V square. Sorry. So this is a thing that we get from the first condition. Now second condition is, so dP by dV, right? So for the second condition, let's write dP dV as RT A by RT by V. Now for the ease of calculation, let's write this function as B function of V. Okay. Now similarly, if you take second derivative d square p dv square here, so this whole thing will become rt e to the power minus a rt by v into a by rt v square into bv plus dv by dv, right? Now so bv is nothing but this thing, right? So this thing is basically equal to 0. Okay, so that means that b function of v will also equal to 0, right? So can take bv equal to 0, so we basically reduce this equation as d square p by dv square equal to rt e to the power minus a by rt by v into dv by dv. So it's equal to 0. Now since this term, now since this term cannot be 0, not equal to 0, so we have to solve db by dv should be equal to 0, right? So now so db by dv you have to now evaluate. So db by dv is nothing but 2 by v. So this is the v by, this is the expression of bv. So if you take the derivative with respect to v, it will give you this minus a by rt by 2 to 2 by v square to v minus b plus 1 by v square v minus b whole square. This should be equal to 0, right? Now you can write this thing in much more simpler way. So that case it will become 2 by v minus b whole cube equal to a by rt 2 by v square v minus b plus 1 by v square v minus b whole cube whole square, sorry, whole square. Okay, now from this equation, right, you have already get an expression of rt, right, in terms of v and b. Okay, so we will substitute that here. Okay, so 1 into, we will be getting 2 into v minus b whole cube equal to v square v minus b 2 by v square v minus b plus 1 by v square v minus b whole square. Okay, now if we do the algebra, this becomes 2 into v minus b whole square equal to 2 by v into v minus b whole square plus 1 by v minus b whole cube. Okay, now so just to calculate, so just to make the calculation a bit easier, you can multiply v minus b whole cube both the side the same way that you have did previously. So sorry, there is a cube, not square. So yeah, so it will become 2 into 2 by v 2 into v minus b divided by v plus 1, right? This is multiplying v minus b cube both the sides. Okay, so in that case the equation reduced to 2 into v minus b by v equal to 1. That gives you v equal to 2v minus b. So v equal to 2v minus 2b, so v equal to 2b, right? So the critical volume Vc is basically 2b right here. So the correct answer would be this one. Okay. So as you can see, this approach is similar, just the way that you have calculated the critical volume for the case of van der Waals gas. Similar approach here, only the equation, state of equation would be different. So the main thing is the dp dv and d square p dv square, both you have to equate it equal to 0. So from the first condition you got this this relation rt in terms of v and b. And from second relation we got this one, right? And from that relation, since everything we have to write in terms of v and v, so we just substitute this expression of RT here into the equation, second equation, and from there we got this expression of the critical volume that is given by 2b. Okay, so this is the way you should calculate. Like now maybe in same type of question, maybe instead of this equation they give some other equations. Okay, in that case also you have to use a similar approach. Okay, now now the next question, question 5. For water vapor near critical point, the vendor was constant and gas constants are a equal to 0.199, B is 1.83 to 10 to the minus 5 meter cube per mole, and R is 8.32 joule per mole Kelvin. Okay, now given this information you have to calculate, find the critical temperature. Okay, this is not a difficult thing to do. Okay, the options are: option A 387.3 Kelvin, option B 643.4 Kelvin, option C 578.4 Kelvin, and option D 491.8 Kelvin. Okay, so uh, the expression of the critical temperature you already knew. Tc is equal to 8 into 27 BR. Okay, now A is given at 0.199, B is given 1.83, and R is already there. Okay, so Tc is simply 8 into 0.199 divided by 27 into B is 1.83 into 10 to the power minus 5 into 8.32. Okay, now simply calculate this. This will give you 387.26 Kelvin. Okay, okay. Now the next question is, for constant volume gas thermometer, the gas is to be filled at, the options are: A is low temperature, low pressure; option B is uh, high temperature, low pressure; option C is low temperature, high pressure; and option D is high temperature and high pressure. Okay. So as you know, we basically want that gas to be follow this gas is basically a real gas, right? That we that I mean the temperature that we want to calculate of the gas, that gas is basically a real gas. But during that formulation of this temperature thing, okay, from thermometric property, right? This one here we basically consider the gas to be yes, this one. So yeah, yeah. So here basically, as you can see here, we have used the equation of ideal gas. Okay, so that means we have to use the pressure and temperature of the gas in such a way the gas, the ideal gas, sorry, the real gas that is inside this thermometer should obey closely to the ideal gas equation. Okay, so in order to do that, what we have basically have to do that we have to basically make the temperature should be high and the pressure should be low, right, in order to make the gas behave like a ideal gas. Okay, so the answer would be at high temperature and low pressure, so that the real gas behaves like an ideal gas. Okay, so yeah, so this is the, yes, the right answer would be this one. Now the question 7 is, the length of the mercury column in a liquid thermometer is 0.06 meter when it is placed in water at temperature 0 degree centigrade. Okay. Calculate the length of the column in meter at the steam point. Okay. Okay. So the options are option A, 0.082, option B is 0.059, option C is 0.120, and option D is 0.694. Okay. The answers are, so we know that, so see, this is a length thermometer, right? So here it uses the length of the length as a thermometric property. Okay, so in order to calibrate the temperature. So we have used, right? So in terms of pressure also, we know this formula, right? P by P. Here it's 0 degree it's given. So P by P0 equal to T by T0, right? So here, this is we know from that constant volume thermometer, right? So here it's length L by, so it's also will like follow same kind of rule. Okay, L by L0 equal to T by T0. So here L would be T by T0 by L0. So here L would be 373 into 273 into 0.06 gives you 0.082 meter. Okay. Next problem is uh, constant volume hydrogen thermometer is used to measure the temperature of a furnace. It measures a pressure of 1 atm at 0 degree centigrade. Okay, at what T it will show pressure 556,781 Pascal. Okay, so here the main units are in Pascal and atm, that you have to be careful about. Okay, so option C is 1300 Kelvin, option B is 1400 Kelvin, option C is 1500 Kelvin, and option D is 1600 Kelvin. Okay, so here 1 atm is, we know, approximately 1.01 10 to the power 5 Pascal. So you can write it accurately like this: 101325 Pascal, right? So here the same formula, so T by, sorry, yeah, T by T0 equal to P by P0. So sorry, T would be 556,781 into P0 is 101325 into T0 is 273. So T will become 1500 Kelvin. Okay, so the answer would be option C. Okay, now question 9. in the interval 0 degree centigrade to 100 degree centigrade, sorry, 660 degree centigrade. Platinum resistance thermometer is used for interpolating temperatures on international scale, interpolating temperature on international scale. Okay, if the variation of resistance with temperature is given by RT equal to R0 1 plus alpha T plus beta T square. This we already know. T is nothing but temperature here, okay, small t. Find values of alpha and beta given R0 equal to 10,000 ohm and R100 equal to 13, sorry, R66, yeah, R100. Yeah, R100 is given by 13.946 ohm and R, the C values of R are mentioned. R 44.6 is 2 24.817 ohm. Okay, so now there are like, to solve this problem we know that the expressions of RT at a given temperature follows simply this relation, the resistance of the wire R naught into 1 plus alpha T plus beta T square, right? So R0, that means at T equal to 0, R0 is given by 10,000 ohm, okay. 10, not 10,000, it's actually 10.0, sorry. It's 10.0, yeah. It's 10 basically, 10,000 ohm, okay. So it's 10,000. So R0 is basically 10, okay. 10 ohm, okay. And R100 is, that is R0, that is 10 ohm into 1 plus alpha into T is 100 plus beta into 100 square, okay. This is R100, so that is 13.946. Similarly, R 4.6 10 into 1 plus alpha into 4.6 plus beta into 4.6 whole square equal to what is the value? 24.817. 24.817 ohm. Okay. Now, so these are the two equations which have basically two unknowns, alpha and beta. Now, so there are two equations and two unknowns. So if you solve this two equation, we'll be getting the values of alpha and beta, right? So if you solve this, solving this gives alpha equal to 4.11 into 10 to the power minus 3 per degree centigrade, and beta is, since the temperature we are considering here is in degree centigrade, so alpha beta should be there also in the units of degree centigrade, okay. And beta is 1.67 into 10 to the power minus 6 per degree centigrade, okay. Yeah. Degree centigrade square, yeah, since there's a square term here. Oh, so it's degree centigrade square. Yeah, so this is the way. The last problem is problem number 10. uh, Platinum resistance thermometer reads 2.57 ohm at 0 degree centigrade and 3.53 ohm at 100 degree centigrade and 2.89 ohm in a bath. Okay, calculate the temperature of the bath on platinum scale. Okay. So we know the options are A 66.6 degree, B 33.3 degree, C 23.3 degree, option D 43.6 degree. So we have already discussed this problem with the platinum scale, right? So this is the temperature in terms of platinum scales, okay, that we have discussed. Okay, so this, yeah, this one. So here, so it also uses the same concept. So here the resistance is approximated up to the first order, and from there this temperature at platinum scale theta is, in order to calculate, we need the temperature at 0 and 100 degree, and also the resistance at 0 and 100 degree, also the resistance at the reference bath, where that bath is basically denoted by temperature theta in platinum scale. Okay, so here, so we have all of this information, right? So the relations is basically this one. So theta we know is 100 into r theta minus r0 by r 100 minus r0. So here r100 is sorry, for r0 is 2.57 ohm, r100 is 3.53 ohm. So just substitute this here. So theta will become 100 into uh, and r theta is also there, right? R theta is how much? So theta is 2.89. 2.89. Theta would be 2.89 minus 2.57 divided by 3.53 minus 0.57. That gives you theta as 33.33 degree. Okay. Answer will be option B. Okay. So that's it. So so we have shown some example problems, so where you can basically calculate from this particular temperature scale thermometer by using different types of thermometric quantity. You can calculate the temperature of the bath of that particular material substance and all. Okay. So this is it. So this is our last problem. So if you have any question regarding today's session, you can ask, or I will close the meeting.
The session was great. I just want to ask something that today question number 4. Can you tell me like where I can find such derivation heavy questions?
Any standard textbook, I guess there are problems regarding this. Okay, or what you can do, you can take these things, right? These equations. Okay, these four
Hmm.
equations we have discussed. Okay, these four equations, and for each of these four equations, you can calculate its own critical volume and critical pressure and critical temperature. Okay, That would be a great
Oh,
exercise. Okay.
okay, okay.
Yeah. Yeah. Okay. Okay.
Yes.
So okay. Thank you for your attention. Okay. So I'll close the meeting now.
Thank you, sir.